Hi everyone, welcome to my YouTube channel. Today we will continue our discussion about finite square wave potential. In the previous lecture, we have discussed about the even solutions of the bound states. Today we will be discussing about odd solutions of the bound states. And the solutions are psi x equals to f e to the power minus kx for x greater than a, d sine lx for the region minus a to a, and minus of psi of minus x for x less than minus a. In the previous video we have seen the solution was d cos lx in the region minus a to a because that was an even solution, but today we will be discussing about odd solutions, so we are using d sine lx, and as it is an odd solution, so we know that psi of minus x equals to minus of psi x. That's why we are writing a minus before psi of minus x for the region x less than minus a. And we have already discussed what is k, what is l. I have just directly written the values here, where k is root over 2me with a negative sign by h cut, and l is 2me plus v naught by h cut. And remember that k and l both are positive. We have already discussed in the previous lecture. I am just reminding you that k and l are always positive, because for bound state energy is negative. That's why we are using a negative sign at the beginning. So continuity of psi at x equals to a gives f e to the power minus k equals to d sine la, and continuity of d psi by dx at x equals to a gives minus ka f e to the power minus ka equals to l d cos la. Now if I divide equation 3 by equation 2, we get minus k equals to l cot la. Now let's multiply a on both sides of the equation, and remember these values from the previous lecture, that z naught is a constant which is given by a by h cut root over 2m v naught, and z is la, where z is a parameter because z depends on energy, because L is given by 2m e plus v naught root over by h cut. Here z is a parameter, and we have already derived that ka is given by root over z naught square minus z square. We have just used these values and parameters in this equation, and we have written ka as z naught square minus z square equals to z quad z, where we have written la equals to z. If we take z out of the root sign, we get minus z naught by z whole square minus 1 root over equals to z quad z, and from here we get minus quad z equals to root over z naught by z whole square minus 1. We are solving this equation by graphical method. Actually this equation 4 is a transcendental equation, and we have to solve it either by numerical method using a computer or by graphical method, but here we are using the graphical method to solve it. How can we do that? Just draw the graphs for quad z and root over z naught by z whole square minus 1 on the same grid and look for the intersection points. So from here we can see that these are intersection point. Let's discuss about two limiting cases. Case 1 is very large well. Very large well means very wide. So we know that Z naught is given by A by h cut 2m V naught. So this is somehow the measure of the strength of the potential or the size of the well. It is defining the size. So from figure we can easily see that if Z naught is very large, the intersection point is very close to pi. That's why we are using z equals to n prime pi. So we can write n prime pi as 2n prime pi by 2, and we can write 2n prime as n, and consider that n is only even number 2, 4, 6 like this up to infinity, and we know z equals to La and L equals to 2m E plus V naught root over by h cut. So from here we get E plus V naught equals to n square pi square h cut square by 2m into 2a whole square, where n is only even numbers. RHS of equation 5 is exactly the energy of infinite square well with length 2a, but here n is even only. In case of infinite square well, we have n equals to 1, 2, 3 up to infinity. It can have any integer value, but here we can only have even values of n. And in the previous lecture we have derived this expression for even solution of bound state, and we have seen that there only odd values of n are possible. So together these two solutions are forming the complete set of solutions like an infinite square well potential. And the second case is narrow well. Narrow well means the value of z naught is very small. So if we decrease the value of z naught below pi by 2, we can see from the figure that if we decrease z naught beyond pi by 2, it is the value of pi by 2. So we can see that there is no chord curve in this region. So there can't be any intersection of these two curves and we can't have any solution. So for z naught less than pi by 2, we don't have any odd bound state. But remember from the previous lecture that even though we decrease the value of z naught beyond pi by 2, we had a intersection point. So no matter how weak the value of z naught is, you always get a intersection in case of even solution. So you always get a even bound state no matter how weak the value of z naught. But in case of odd states, you can have a bound state for the value of z naught less than pi by 2. So I have written z naught is equals to a by h cut root over 2m v naught, and from here I have derived a condition for v naught, which is v naught less than pi square h cut square by 8m a square. So if the value of v naught is less than this amount, we can't have a bound state solution for odd states. That's all for today. Thank you for watching my video. If you like it, please subscribe and share. See you in the next lecture.